Welcome to CSC 201, section 11.1, real valued functions of a real variable and their graphs. A lot of this is going to feel like a review from college algebra, if you took that at GCC, or maybe algebra 2 of what you took in high school. But we're just going to go through it, review it, make sure we all know this material. So a real valued function of a real variable is a function from one set of real numbers to another. If f is a real valued function of a real variable, then for each real number x in the domain of f, there is a unique corresponding real number f of x. That's just the definition of a function, right? For each x in the domain, there is a unique corresponding number in the codomain, f of x. And the graph of f is the set of all points x comma y in the Cartesian coordinate plane with the property that x is in the domain of f and y is equal to f of x. So we're going to start with a simple formula called a power function. Let a be any non-negative real number, and we're going to define p sub a to be the power function with exponent a. So p sub a of x is just x to the a for each non-negative real number x. So I'm going to sketch the graph of the power functions p0, p1/2, p1, and p2. So p0, that means x to the 0, which is 1. So this is just a horizontal function at a height of 1, which is about right here. P0. Okay, and then P1, actually they do P1/2 next. P1/2 is x to the 1/2, which is the square root of x. And we can just pick some convenient x values to plot these points. So the square root of 0 is 0. The square root of 1 is 1. And then the square root of 4 is 2. And the square root of 9 is 3. So there's our square root function, the p to the p sub 1/2. And then p sub 1, that's just x to the first, which is x. And so y equals x would go, maybe I'll switch colors so we don't get confused. 1, 1, 2, 2. 3, 3, 4, 4, etc. So there's P1, like that. And then finally P2 would be x squared. So that starts at 0, 0, then 1, 1, then 2, 4, 3, 9, and that's enough to get a picture of this graph. So those are the power functions with powers of 0, 1/2, 1, and 2. The floor function is a function that rounds all numbers down to the number below. So the floor of a number is the integer immediately to its left on the number line. Or in the case of an integer, just the number itself. More formally, the floor function is defined by this rule. So f of x, and then we use this symbol. It kind of looks like absolute value bars, but it has little feet for to indicate floor. And we define this thing as the greatest integer that is less than or equal to x. So the largest integer that is still smaller than x. Or the unique integer n such that x is sandwiched between n and n plus 1. So I want to sketch a graph of the floor function. So let's just start with numbers between 1 and 2. Okay. Any number between 1 and 2, the floor of it, you're going to round. So maybe we'll make a little xy chart. We'll make a little x and the floor of x chart. Okay, so if I do like 1 when you round it, any way you round it, 1 would be 1. So the round down is 1. All right, and then like 1.2, that would be 1. 1.7, normal rounding, that would go up to 2, but the floor function takes it down to the integer below. So that's also 1. 1.9, 1. And then as soon as you get to 2, it jumps. Okay, so let's see, 1 comma 1, and then it stays 1. The output is 1 for all the x's between 1 and 2. So all these x's are going to give me 1 as an output, but not 2, right? When I get to 2, it jumps. So I'm going to put an open circle at 2 and say all these x's in between here. If you plug in any x between 1 and 2, it's going to give you a y value of 1, but not 2, because when you plug 2 in, the y value is 2. So I have to make sure to do the open circle and the closed dot so that this will pass the vertical line test and be a function. Now all the values between 2 and 3, like 2.1, 2.3, 2.6, 2.8, those all get rounded down to 2. As soon as you get to 3, it jumps. Okay, so all the numbers between 2 and 3 have an output of 2, but as soon as you get to 3, the output is 3. So this is, you can kind of see the pattern developing. This is also known as a step function. And I can go backwards as well. Like that. The ceiling function is defined similarly, but the ceiling of a number is the integer immediately to its right on the number line, or in the case of an integer, the number itself. The notation for the ceiling function, it's similar to the notation for a floor, except that instead of having feet, it has little hands at the top. So it's the ceiling of x. And it is the least integer that is greater than or equal to x. So for example, the ceiling of 1.4, is 2. So think of it as a round up function. Always goes up. Okay, if f is a real valued function on a real variable and we let m be any real number, then the function m times f is called the multiple of f by m, or m times f, is the real valued function with the same domain as f that is defined as m times f of x is just m times f of x for each x in the domain. So f of x, those are the y's that are associated with each of the x's. So we're just multiplying all the y's by some multiplier m. And you may have referred to this concept as a vertical shrink or stretch of a function in a previous course. And you probably studied other transformations like shifting left and right and up and down and vertical stretching and shrinking and reflections. For this course, we're only studying the vertical stretch shrink. So for example, we have a function whose graph is shown below, and I want to sketch the graph of 2f. So to sketch the graph of 2f, we just double all the y values. So I'm going to make a little table of values. So I have x, y, and I'm just going to put in the points. Because this is piecewise linear, I only need to know the points, and they completely define the lines. So this first point is at -6, -2, then -3, 0, -2, 2, 0, -1, 2, -2, and 6, 1. All right, so now when I want to calculate 2f, I'm just going to double the y's, because this y really is f of x. So 2f is 2 times the y. So now my y's are just going to get doubled. So I have -4, 0, 4, -2, -4, 2. So I took each of these y's and just multiplied by 2. Now I'm going to plot with my original domain, the original x's, I'm going to pair the new y's, the doubled y's. So I have -6, -4, -3, 0, -2, 4, 0, -2, 2, -4, and 6, 2. And then it's piecewise linear, so I just need to connect the points with lines. And you can see that vertically what happened is that I stretched the graph of f. I doubled it. It's twice as tall. I stretched it by a factor of 2. Okay, the last concept that we're going to review from a college algebra type course is increasing and decreasing. So this is the formal definition here. It says that for all real numbers, x1 and x2, if x1 is smaller than x2, then f of x1 is smaller than f of x2. That tells you that a function is increasing, right? Because as you go from left to right, so x1 smaller than x2 means this is further left, this is further right. Then the y value on the left is smaller than the y value on the right, and we're going uphill, and vice versa for decreasing. But the way you can just look at a graph and see this is you read it from left to right, and you say uphill or downhill, right? So I'm going to start at the left here, and as I'm reading left to right, I'm going downhill. So this function, which is the absolute value function, is decreasing here, and then as I start moving uphill, it's increasing. And when you describe where a function is increasing and decreasing, you only give the x values. So for absolute value of x, it is decreasing for x values from -infinity to 0. And then it's increasing on x values from 0 to infinity.